in
laver, je le nettoyer, je changeais les couches et les contents se sentent très bien. Et, et je viens te dire qu'il t'a invité de boire une...
Good afternoon, everybody.
Afternoon.
Thanks
Good
for
afternoon.
coming to this tutorial. For your information, this tutorial will be registered and made available to the entire audience afterwards in case you cannot manage to attend the full event. Okay, so let's start. It's 3 o'clock sharp. My name is Silvio Abrate. I am from the Links Foundation in Torino, one of the partners of the STARS project that has organized this event. The purpose of the project is to help SMEs in the railway sector to go digital as fast as possible. And one of the activities that we're carrying out in this project is to deliver focused tutorials on the adoption of advanced technologies in the railway sector. This tutorial is about the use of digital twin in the railway sector, and the agenda is as follows. I will give this quick introduction of a few minutes, then I will hand over to Florence Masbernat from the Railenium Technology and Research Center from France that will discuss the importance of the digital twin according to a technology analysis that Railenium made about the impact of technologies in the railway sector. Then we will hand over to my colleague Edoardo Pristeri that will stay with you for roughly 1 hour and a half, explaining what the digital twin is, what kind of competencies are needed, and we'll give a sort of hands-on and we'll show a practical application of the use of a digital twin for predictive maintenance. And then we will have some time for Q&A and we'll jump to some conclusions. So just to give a very quick idea, a very quick hint on why we are here discussing about digital twin that are one of the pillars of artificial intelligence. I'll give you an example of what artificial intelligence is doing in other sectors. And I'm starting a video showing an example of a kind of generative artificial intelligence model that has been that is emerging in this month. So what I'm showing here is a generative artificial intelligence engine for graphic application. This is a prototype that is available for test more or less for everybody. What did we do with this engine? We are asking this artificial intelligence engine to draw a portrait of a programmer using its computer, like if it was made by Renoir. Okay, so in a matter of seconds, this artificial intelligence engine is drawing a Renoir-like painting of a programmer in front of a computer. Okay, so this is what artificial intelligence is able to do today. So imagine you are a novel writer. You might think, oh, funny, I don't need to hire any graphic designer anymore. I can deliver my book all on my own. Imagine you are a graphic designer. If you've seen this coming, maybe you can use it for producing many more drawings in the same time. But if you haven't seen this coming, you might lose your job at all. So this is exactly why we want to introduce this topic to you, is that because we need to see this coming and to be prepared to leverage on opportunities and to counteract to problems. So let me now hand over to Florence for discussing the technological analysis on the railway sector. Florence, the floor is yours.
Okay, thank you very much, Silvio. I'm going to try to take it. Okay, is it okay, or do you see?
That is the view for the referent. Maybe you could.
Okay, no. Oh, sorry. But I don't know, because I have. I would like to put it in the diaporama. Okay. Anyway, I hope. Okay, yes, I will try like this. So I will introduce now the technology innovation analysis that was conducted by Ralenium for the STARS project. And just to remind you what was the objective of this technical innovation analysis. First, it was to provide all the SMEs, part of STARS, and an overall picture of the railway major innovation trends and the advanced technology paths that are associated to be able to implement them. So we hope that this objective is to contribute to enhance the awareness of the SMEs and the capabilities to adopt those advanced technologies, and also contribute to identify what are the railway industry challenges and the associated innovation roadmap. So it's also to highlight some key aspects and also the relevant skills that should be considered. So here is the methodology we have used for this analysis. So, well, it's divided in 4 steps. So the first steps was first to source and to select the documents that describes the railway major innovation stakes and that provide, in fact, the state of the art from the whole R&D industry and experts of the railway domain. So you can see that it was based on, for instance, the ERCI strategical document. So ERCI is a European Research Advisory Council that provide a European roadmap based on the including, say, the major, of course, railway actors, and the second strategic document is SRIA, so the Strategic Rail Research and Innovation Agenda, that was also associated to that. And you know perhaps about the Europe's Rail Joint Undertaking that has been launched and in continuity of the Shift Rail Joint Undertaking, and that also reminds what are the major area where rail should put the effort in order to really manage major innovations. And so from that, we identified then the changes that are according to all this technological ecosystem, and we extract the innovation trends and the technological challenges. And then we try to detail the list of the technologies and to propose a relatively large list of technology to cover those changes. So you can see that we have at the end detected 8 innovation trends and around 37 technological challenge on both sides. One side is hardware and the other one the software. And the last part of this methodology is to identify what are some key variables that we have proposed to. We have selected, in fact, some key indicators that should reflect the gap to be filled by SME if they want to tackle all those changes. So we selected from those key indicators the time to market first, but regarding the level of maturity of the technology at the time, because of course it's very important to consider at which time you should have provided your development. And the second are the skills. Of course, that's also very important because we know that digital technologies will involve very new skills that are developing, but that may be sometimes rare, so it should be considered also as an important investment. And of course, the nerve of the war, that is a budget to engage. Sometimes it can be low, see if you have already the technology at disposal or more high. And so we have a scale quotation from 1 to 5. 1 is low investment, I would say, and 5 will be high. So what are these 8 innovation trends that we find out at the end, meaning that we should reach this in 2030. So the first one is what we call it smart asset management and maintenance of the future. And this is one I will develop more. I will go inside this to illustrate, we say, where the digital twin or artificial intelligence are, how they are important on this field, for instance, but they are also in other fields. So we can see, for instance, the automated area where you need to have autonomous train operation. An asset for this, that is a second innovation field. A third one, also very important, because we need to optimize, of course, the capacities of the infrastructure regarding the train traffic. So it's concerned the traffic management, the planning and control of it. Then another important topic will be the grain freight logistic chain. And this is an important area where we need to also increase significantly the market part of the freights during the next years. And field that is named Railways Digital Twin Simulation and Virtualization, where you can see all around the question of the development of digital twins, and then also the aspect 6, the IT6 regarding the regional rail services, and specifically the capillary lines. For instance, you have in France a large program of innovation that aims to be able to use more those capillary lines that are a significant part of the railway networks and that are very useful for regions. And then the IT7, the sustainable and green rail system, of course, with the question of the energy management and efficiency, and as well as the capability to be green and with an eco-friendly whole system. And the development of multimodal and intermodal transport, of course, that are also important to maximize not only railways, I would say, efficiency, but other modes as well. So I would just make a little focus because it should be very long to comment all the results and all the metrics, but to illustrate this on the first, I would say, topic. So here you can see the matrix that synthesize the methodology that I was presenting to you, and with I would say several columns. So I will comment a little bit. So you have the innovation trend identification, and then the title. So here we are in the first one, that is a smart asset management and maintenance of the future. So you can see that it concerns most part of the railway system, covering the operation, but also the rolling stocks, infrastructure, or even control common systems. And here you can find what should be the role, for instance, of SME, what can be expected in this for this segment of the railway system. So first, it would be to develop components with self-diagnostic that should be suitable to send interoperable data to other devices and subsystems, and also with the requirement of a very low energy consumption. See, it's important also topics energy. And you can see here different technologies that have been identified, listed, and on the hardware side and on the software side. So upon that we will need, of course, IoT sensors, for instance, for rolling stocks. We will need to develop software application to manage IoT real-time, for instance, big data, but also strong machine learning software that should be able to really predict for instance, the failure, and being sufficiently robust and precise, so that we should automatize, for instance, the maintenance intervention, and of course, with more accuracy, more safety, and less intervention of people. So on the second part, you see also that we need to develop highly performing inspection tools, also that should be more efficient and more rapid, and as I say, with a capability to have real-time results very close to reality. So for this, we will need clearly to develop, among all the technology that probably you know, like cloud computing and so on, to really develop a digital twin for monitoring this asset and ensuring the continuity of all the data chain. And associated to this digital twin, we need also to have, for instance, digital image processing. It will have to be very performant, machine learning algorithm, but also data fusion algorithm and other decision-making tools. So, in fact, you are combining several tools in order to provide at the end a digital twin that is the more close as possible of the reality. And this is we will be, of course, to have this software model that should be able to represent the reality. And to illustrate this, just because I know that further in this presentation you will have much more other examples, but just to illustrate one that was developed by Ralinium regarding IMAD, that is ultrasound sensor smart data processing. So you need to have first to detect, for instance, squat and HX within the rail. We first have the first development of a laboratory prototype, where you have here a mobile transducer. You will make measurements, and then you will need also to develop your data processing, your intelligence artificial processing based on accurate methodologies, and also to challenge it, of course, on the rail, because it has to be very robust and to be able to face the very, I would say, hard and constraining railway environment. So this is about, yes, which kind of challenges are we have to face. Do you think it's okay for me, Silvio?
Thanks, Florence. We can hand over to Edoardo for going into the technical details of the digital twin. So, Edoardo, it's up to you now. Please make sure you share the presentation mode.
Sure. So, are you seeing the correct screen? Perfect.
Yes.
Okay, so let's begin this journey across the world of the digital twin. First, maybe I can introduce myself. I'm Edoardo Pristeri. I am a researcher at Links Foundation. I've been here for the last 4 years, and my topics of research besides digital twin are software development, innovative software development procedures. Also, I work in a group which develops DevOps applications. For the people who don't know what this is, it's like innovative methodologies for optimizing the development and deployment of software across different environments. So you see, this is quite relevant with the topic of the digital twin. And also I work on ML ops applications, which it's a similar concept, only applied to machine learning models, which are another important topic when talking about digital twins. Also, I worked on several EU finance projects, such as SafeCare, European Factory Platform, Knowledge Project. And I tell you this because later on in the presentation, I will give you an overview of several assets that have been developed, not only from myself, of course, but from our whole research group. And we see how software can be integrated, and so how different software can be seen as a building block of a digital twin, which is something that now we will head on. Just let me give you one last overview of my research area. We work across several domains, starting from cybersecurity to wireless communications. These two topics are particularly relevant since some of my colleagues working both in cybersecurity and wireless communication will hold 2 of the next STARS tutorials, so don't miss them on cybersecurity, on IoT applied, and on 5G. Myself, I work on computer vision, data quality, digital twin, of course, and data exploration. So let's begin today's story about the digital twin. We will have first a brief introduction of what a digital twin is, and a bit of history about the digital twin, which I think it's useful to understand better what we're talking about. Then we will go through some high-level definition and concepts to switch then to what are the actual advantages and benefits, which I think is why you're here today. I've reflected a lot on how to present this to you today because you're quite a varied audience. There are many different roles, and so we will have some more high-level concepts and some more technical concepts. Let's start, so as I said, with the history and from what is actually a digital twin. The concept of the digital twin, I've had to make some research about this because I wasn't up to date with the history, because I usually work on more like technical issues. And the concept of digital twin, it seems that it dates back to a presentation to industry in 2002, made from the University of Michigan. And this presentation was about the formation of a product lifecycle management center, a PLM center. I found this figure, which I think represents, it's more than 20 years old now, but I think it still represents quite well what is the digital twin, what is the overall idea of a digital twin. Because here we have already all the main elements of the digital twin, which are the real space, the virtual space, and the link for the data flow from the real space to the virtual space, and the link for the information flow from the virtual space to the real space. And also we have the concept of the different sub-virtual spaces, which we understand later on what we're talking about. The premise behind this model was that each system consists of two systems. The physical systems that historically has always existed, and a new virtual system that contains all the information about the physical system. This means that at the time, obviously, it was just a concept. They were trying to create, let's say, a mirror or twinning of systems between what exists in real space and what exists in virtual space, and vice versa, obviously. So let's switch to the real system. We have these physical models that, as we said, they've always existed. The problem is that physical models are very useful and they date back to Leonardo da Vinci, so quite a strong concept. But they give only information about the appearance and maybe some of the features. But to get many more information, then you need equations and you need math to model some of the feature, and some of the feature which are not easy to be modeled with equations, but in the traditional way cannot be modeled at all. So how do you understand how a physical object behaves? You have to create models which are costly to maintain, and they get ever costly as the complexity of the model you want to build increases. They are time consuming because creating a model takes time. Even taking out all the phase of planning, even just the construction of the model takes time. And most importantly, they are very difficult to upgrade and to scale. Because, for example, if you want to, let's say, change a feature, then you can't. You have often to go back to the planning stage and plan a new model and create a new model. And so you see how this not scale at all, because it's not simply about the geometry of the product itself. It is basically about the behavior of these things and how we can connect this model in the physical space to the predecessor of the virtual space where we have equations and math. This was the challenge. So nowadays we are still in the middle of the revolution that can be described by the Moore's law. Because here you see we have this graph on a logarithmic scales, which puts the computing power of every CPU starting from the year 1970 to 2020. And you see that it grows on a perfect logarithmic linear scale in a logarithmic plot. So this means that we are talking about exponential growth. And this exponential growth means that bits, so the fabric of the virtual world that we've seen before, are getting cheaper and cheaper every day. While many of you working in manufacturing will know, of course, the atoms, so the physical models and the physical objects, are getting more and more expensive because they are every day more and more complex. So this transition from the old paradigm of working with physical models to a transition which is based on virtual model makes more sense than ever today. I think that we can agree on this. And so we are moving towards virtual twins. So from the real space to the virtual space. And so going along the history of the digital twin, we skip from, sorry, someone is moving the slides. Oh. Okay. So where are we? Yeah, we have moved to the virtual twins, and we can go forward with the concept of the digital twin, which was improved along from we started in 2002. Then we moved to 2005, where this first concept was referenced, and the history goes along up until 2011. It was when we have not confirmed, but this is what I found. This first reference to the digital twin, to actually the digital twin, in a paper by a sub-agency of NASA, because of course it was the actual rocket science driving this revolution, because here we are talking about some of the most expensive manufactures made by humans, and so it made a lot of sense for them to be precursors on this revolution that is still happening today. But for them, the trade-off of the cost of atoms and the cost of bits started to make sense. Nowadays, it's already 10 years ago. So the goal for them and for us today, it's still to move the whole design process from atom to bits and to design a product already with the virtual space in mind. Because when we do this, when we design with the virtual in mind, we enable all the benefits that the digital twin provides when we actually have the product released to the users. This is important to note, because basically what you want to do is to design the product virtually. So stop making pen on paper drawings. Once we have done this, we want to test the product virtually. So we want to stop making wood and clay models. For example, I think of wind tunnels. This is very costly to do, and we want to move as much as possible to the virtual. We want to manufacture the product virtually, because as the complexity of a product grows, I can make some examples on this. We are involved in different research projects focused on this. There is the need to reconfigure the production line to adapt to the evolving characteristics of the product. And so while you are developing a product, the product changes, and you have to manufacture test batches. And so you really want to be able to move the manufacture to the product virtually. This means you want to have simulations of the manufacturing line, of the production line, to check what is the, let's say, the optimal way, but at least what are the least expensive configuration of the most efficient configurations of your production line when you manufacture test batches of a product. And you want also to support the product virtually, because you can start experimenting how the product will behave. And since we are talking here today about railways, all your products have a life cycle which I think it's in the order of at least 20 years. And so you have to plan for this, because it's not just that you release a product and then you forget about it. You want to take care for the whole life cycle of the product. And so you need to be on top of this. And only when you have clear all the steps that you need to take with the product, so the design, the test, the manufacturing, and the support, only then you can start moving to the atoms. So you leave the virtual world. You have saved a lot of time, because simulations are getting faster and faster. You have saved money because you have produced less atoms. And then, of course, we are not yet in a completely digitalized world. We hope to get there someday, but we are not there yet. So you move that to atoms. And so you have to make this analysis, but I think that for many of your production processes, the cost of information, of obtaining all of the information, of processing all of this information will be less than the cost of having, let's say, wasted resources, because obviously the design phase, it's still a lot based on trial and error, especially on more innovative projects. So another example of the advantages of this, it's I think it applies to the railway sector as well. It's crash tests, because when you create a new train or a new component of a train, then you need to perform crash tests to ensure that this component behaves in a safe and reproducible way when the unexpected happens. So you can take your vehicle, your train, and you can crash test in the physical world, but this costs a lot of money. And so you want to move it to the virtual world, where you can crash over and over and over again, testing a lot more possible situations, and only act in the physical world where you find that you have really the need to move to this more expensive world. I think that now we are ready to state the actual definition of the digital twin. The digital twin is a set of virtual information, I'm reading, that constructs the virtual information constructs that fully describe the potential or the actual physical manufactured product from the microatomic level to the macrogeometrical level. This is, I found the reference. This is what was stating in the NASA paper from 2010. So it was 2010. They were investigating about the concept for next generation fighter aircraft and NASA vehicles. So you see that these are very expensive products, and made a lot of sense for them to do this analysis. So once that I think that there is someone unmuted. Okay. You see that at the optimum, any information that could be obtained from a physical manufactured product, then we would have it in our digital twin. But of course, this is not always the answer, because this is a very high level definition, and so this does not always make sense, because you don't have to think that you have. I think if you're building complete carriages, obviously you don't see the value in having digital twins of every screw that composes your carriage, every piece of metal. This would, of course, be too complex for what you're trying to achieve, because maybe you don't need some of the information. You are interested only in some features, and so we can move to some more detailed definition of the digital twin. Here we divide the digital twin into 4 different categories. We have the digital twin prototype, the digital twin instance, the digital twin aggregate, and the digital twin environment. These 4 categories have been defined because, of course, you don't always need the power of having the complete model of your product accessible. Maybe you need only some higher level monitoring information, or you just need to have more information about your fleet. But I go back just 1 second to the first slide. You see, these you can always go back to this overall case where you have a real space and the virtual space where you can do planning and strategies. This is already a digital twin, even if you don't go down to bolts and screws. So the first digital twin, the prototype, it's the one that I have mostly already described. This is the type of digital twin that describes the prototypical physical artifact. This contains the information sets necessary to describe and produce a physical version that duplicates, or twins better, the virtual version. These information sets can include, but of course they are not limited to these. I have thought about the manufacturing world, but you can move this also to other categories. But for example, the bill of materials, the bills of services, the bill of disposal. So it's like what I said, when you plan for the planning, the testing, and the life cycle, the whole life cycle, including the disposal of a product. So this is the more detailed digital twin, the kind of digital twin that needs to have more information about the physics of the object, and that you need to have if you want to manufacture with the concept of the digital twin in mind, and that will by implementing it provide already all the other digital twin categories that I'm going to explain. The second category is the digital twin instance. This type of digital twin describes a specific corresponding physical product with an individual digital twin linked throughout the life of the product. This is probably the most common, let's say, category of digital twin, the one that most people have in mind when thinking about digital twin. depending on the use case, this type of digital twin usually contains the 3D model that we are used, as I said, to see with general dimensions, the bill of materials, the bill of processes, and also all the results of the lists of the operations of the measurements that have been performed on the real twin, because as the name says, the instance, we need to have one instance of this digital twin for each of the products that we have in the real world. And so this digital twin will contain, let's say, a service record that will describe all the services performed, the components replaced, operational states captured from sensor data, current, the past, obviously for the history. And on this digital twin, we can also apply prediction services, so that according to the history of the single manufacturer, we can predict its evolution and how it will behave. From this digital twin instance, we can then move to the digital twin aggregate. And this type of digital twin, it's what we have when we think of, for example, fleet management applications. When you think about micromanaging all the elements, I think of a railway company that wants to manage all these trains, then they plan on building a digital twin aggregate, because that they will have digital twin instances of each single train. Of course, if they are not interested on running very detailed operations on every single train, they will probably be not too detailed, but they will have, of course, at least one element representing each one of their physical assets. And the digital twin aggregate will be the aggregation of all the digital twin instances. But unlike the digital twin instance, the digital twin aggregate doesn't have to be an independent data structure. So maybe it may not be a physical computing resource. So when we think about a digital twin instance, we think of a software module, central software module connected to a database. I'm saying a very high level, very basic architecture, but we usually have this core module, a database, and this core module is connected to like a message bus software, which is connected to all the sensors on board the element, and also connected to the remote database, which contains all the information about the history of the manufacturer. And so this central element is in charge of running, for example, simulation, so on, to have different service enabled on this digital twin instance. On the other hand, the digital twin aggregate doesn't have to be structured this way, but it just may be a computing constructor, so a more abstract paradigm that has simply access to all the digital twin instances and can make queries to either a single one or to all of them proactively, possibly, so that when, for example, the end user, in this case, queries for the mean time of failure of component X, in this way, the digital twin aggregate should already have the data which is required to give an answer if this information is collected, obviously. And continuously examine sensor readings coming from all the different digital twin instances to enable also predictive maintenance application and so on. But it doesn't have to be a centralized module storing all the data in a single place. This is not advisable, and it's probably not the best way to do so. In the end, we have 1/4 digital twin, which is probably the most complex digital twin that we are going to discuss about today, which is the digital twin environment. The digital twin environment, as I've written on the slide, it's an integrated multi-domain physical application space for operating on digital twins for a variety of purposes, such as interrogative, predictive, and learning. What am I trying to do? That often a digital twin it's not enough on its own, and here I'm talking about mostly about prototype and instance digital twin, because these digital twins are only useful to model the product that you're manufacturing and that you have built a digital twin of, but they don't give you information about how this digital twin, how this product behaves in the real world. So this is why digital twin environment exists, because they are a framework that can enable the interaction of these digital twins in the space where the product will operate. For example, I was talking with Silvio a couple of days ago discussing these slides, and an example relative to the railway world came to my mind, and it is about, I won't go into detail, you are for sure you know better than me, but it really caught my mind, and because a couple of years ago, Ferrovie dello Stato, Italian railway company, let's say, bought some trains from the Netherlands at a very discounted price, because apparently these trains were really good trains, but they had troubles with snow and with the cold weather that made them really behave not great. And so they couldn't operate these trains in that environment, and so they had to sell it and have a loss on these trains that now operate in Italy in mild weather, and so with less stoppages. This is the end goal of having a digital twin environment, because you can't just make a very good product. You also have to consider how the product interacts with the environment. So let's move to what you can do with digital twin. There are three main goals that you can achieve by implementing digital twins, which are predictive goals, interrogative, and learning goals. I will give a brief description of each goal. The predictive is when the digital twin is used for predicting future behavior and performance of a single product. We have somewhat already discussed this at the prototype stage. For example, some recap. The prediction would be, for example, the behavior of the design product with the different components that vary between tolerances in order to make sure that that the design product meets the proposed requirements, while at the instance stage we move from one digital twin to the other. An example for the predictive behavior of the instance digital twin is that the prediction would be applied to a specific instance of a specific physical product. So as we said, we want to know how this product would behave from the current point in the product release cycle and from the current state, and we move it forward. And so we can also use different instances of a product to have a range of multiple possible states. That this is where the real advantage of a digital twin comes into play, not to have a single product, but to have many, so that you can also have like a probabilistic approach to predictions, which is always the best thing to do, because predictions on a single product don't tell you much. You can really get some useful insight when you scale this approach to many different digital twins. The second, it's the interrogative digital twin, and this applies so to the digital twins instance as part of the digital twin aggregate. And so in digital twin instances, as we said, can be interrogated for the current and the past histories, irrespective of where the physical counterpart are in the world. You see the value of this. You can check their current states. So if we are talking about trains, for example, I think of fuel, of the throttle settings, where are they located in a geographical location. And also you can check for their physical characteristics, so that if you have made sensor on the link between the different carriages, you can check for structure stress or really any other characteristics that was instrumented. Multiple instance, of course, provide data that correlates for predicting future states. And so we go back to the predictive. You see how all of these goals are interlinked. And so you can mix the two and correlate component readings. So interrogative, because you ask the product, with recorded failures. And so you have these two elements, and you have alerts, of course, when these things happen, but you can mix those two and then have a predictive approach. And so you have the history of the sensors, the history of the failure, and you can go on having predictions of the single failures. Lastly, we have the learning goals for a digital twin, because when you deploy digital twin, you can easily get a virtual model that reflects the performance of the object or system and the real-time data. And this is very useful when you have different iterations of a product in the real world. Because you can, in the real world, if you don't have any sensor on an object, you can't really be sure of how this object, if you don't apply simulations, you can't really be sure what are the differences between two releases of a product between two different versions. The learning goal is to get these insights, and so to transfer the knowledge that you have already acquired from some components that stay the same between two different versions, and also when you are monitoring these two versions, you can really see if the development is going in the way that you planned for your product. Next. I think that if you're here in this webinar, you may be interested in building one. So now that we have seen what is a digital twin, let's switch to what are the main skills and building blocks required to build a digital twin. So we start from the IoT because IoT is the backbone for digital twin because it provides the connection and the access to data and intelligence in the physical world. IoT devices and sensors can collect, as you know, and transmit data from the physical system to the digital counterparts. And so they are going back to the first diagram that we saw today, the hooks of the virtual world on the real world, because they enable this virtual world to collect and transmit data from the physical systems, and they, as we already said, enable real-time monitoring, analysis, optimization. And also IoT, it's not only relative to the collection of the data, but IoT also works in sensing, in applying the changes that the digital twin has modeled back in the real world. And it allows this actual, it's the enabler of this control loop that we may want to implement. There are two types of IoT sensing networks that we will mention today. It's a very high level overview, but it's important to make a difference between the IoT that senses the activity of the product. So we might think of vibrometers, temperature sensors applied, for example, to engines and so on and so forth. But also, as we said, it's very important, especially for building the environment digital twin, to have as well IoT sensing the environment in which the product works. So in the railway sector, if we want to make an example, we can think of both the IoT that we have on board of the train and the IoT that we have on the railway, on the tracks. And so you can understand how it's important to correlate this information to better understand how a product behaves. Next, we move to the data acquisition and pre-processing. And so again, we have the real world, we have the virtual world, and then we have a link. Here, we are talking about the link between the real and the virtual world. And it's very important because I will spend some time on this. Implementing a good data acquisition processing pipeline can increase the trustworthiness and the value of the digital twin, because if you can't trust the data, of course you cannot make good decisions, and it's risky to make optimization, to make actions on data you don't trust. And also, having these pipelines can help you to understand and address the data quality issues such as completeness, correctness, consistencies, timeliness, and relevance. But we will have a focus on this later because it's a very dear topic to me. And as I said, this is important also if you are planning for digital twin to understand if you're placing the sensors in the places where they can give you more value. Because, for example, if I place 4 different temperature sensors on a single component of an engine, through data acquisition pipeline, I can see that there is a very high correlation between the values read by those sensors. And so these sensors are not giving me any value. They are only me costing money, both in the physical world, because I have to actually buy and install these sensors, and also in the virtual world, because I have to store the data which comes from these sensors, and this is all wasted money. So implementing a data quality pipeline as a bridge between IoT and AI can really save you money. And in the end, as we said, it can ensure that that AI application meet quality requirements and expectation of all the different stakeholders, such the users, the developers, the product developers, the regulators, and to a certain degree to society as a whole. Because it's important to note that when we talk about AI, we are often talking about a black box. We will go deep later on, but AI it's simply a black box more often than not. And so when we're talking about black box, what stands it's the saying garbage in, garbage out. If we are feeding AI with data with low value, we will get low value hints from the AI. This is important to note. This is probably the ugliest slide in my deck. Sorry about this, but I really want for this message to pass that when implementing digital twin and feeding data to digital twin, you have to check for at least all of these points to be valid on the data that you are collecting. Otherwise, you're probably wasting some time and money because it will have low value all of your simulation and all your methods applied to the digital twin. You have to have syntactic checks, so the data has to stand with its own format, because otherwise it can't be processed or has to be processed in a different way. Semantic checks, similar, you have to ensure that this is applied. Completeness check, you have to make sure that the data is as complete as possible, because you have data filled with missing values. Again, you need a lot of more data for coming to the same results, because you have to infer what's missing. You have validity checks, of course, because the data is not valid, then it's just adding noise and issues to the predictions. And yeah, I don't need to go really through all this, but I want to make sure that you're understanding what I'm saying, trying to say here. Consistency, accuracy, uniqueness. You really want to address these steps before you store the data, because if you do it after, it's much more difficult and expensive to deal with this. Last block, we have talked about the real world, the link to the real world, the data, and now we have in the virtual world. And so at the core of the digital twin in a virtual world, there are all the different sub-virtual worlds, which are AI models and simulations. These are the way that we implement to make the computer understand the complex phenomenon that govern reality and that you want to try to simulate. As I said, all the AI models are data-centric, and the AI models learn patterns and rule from the data without knowing the underlying processes. This is why I was really stressing about the data quality concept, because if you don't understand this and you start feeding, if you try to save money and some time on data quality, you're just feeding the AI models data which with wrong patterns and rules that actually don't apply to the real world. And so the AI will never be able to really understand the underlying process. On the other hand, the simulations are process-centric, so these are, let's say, the grandsons of the math formulas that we once had to calculate by hand, and we all had to calculate by hand at our physics exam. And so this is when we know how a process works, and with math, usually we try to recreate this process as it's written using mathematical models. They have different goals. AI models can be used for tasks such as classification, prediction, recommendation. So again, when we don't understand the process, on the other hand, simulations are used for testing, validation, optimization, and so on and so forth, where we have a better idea of the physics governing the process that we're trying to simulate. Now, with this next slide, my goal is to scare you. This is the digital twin reference architecture made by IBM. I chose this because nowadays we aren't yet at the stage where we have solutions coming from big players, or comprehensive solution coming from big players, which cover all the required skills for implementing a digital twin in the real world. We are past the concept phase, which was from 2002 to 2010. During the last 10 years, as the computing power has improved, there was the experimentation phase, so we switched from the idea to the first actual implementation. And now the way we see it is that in the next 10 years will be in the standardization phase, because we will have to go from the single building blocks, which are still currently being experimented by research institutions such ourselves, the Linux Foundation, and many other players in the world. There are already some suites available, but they are most often not complete, and they don't provide interoperability. This is really what the focus will be in the next years. And so here you see that a lot of different skills are required for implementing a complete, let's say, digital twin. We have the whole competence in the IoT stack, sensors, gateways, so on and so forth, IoT. Then we move up to the data stack, and here we have all the expertise that I tried to make a summary of regarding all the both the data quality concepts, but also the whole data modeling, because you often have to use models and schemas to make sure that your data is coherent and it represents the problem you're trying to achieve. Then we go up, and then we have this complete stack of more company-related processes. Up again, simulation, so that you need a lot of math competencies and physics competencies. You move up again. You go to AI. You have passed where you have reached the point where maths is not helpful anymore, and you have to switch to statistics to understand processes that you don't really understand. And then again, you have to move up, because when you have the results from the simulations and analytics, which are based on the data which has been collected from the IoT, you have to visualize this to give value to the end users, because otherwise end users can't really manipulate directly simulations and the AI models. So you have to make this human readable. You have the whole competence of VR, AR, 3D and 4D, eyeball reading, all this information, let's say the whole metaverse thing. And then up again, you have the process management, because you have to govern all of this information. You see this really gets complex and scary. And also you have these vertical stacks of integration, because you have to integrate all of these horizontal layers. You have the governance layer, because you have to make sure that no data is leaked in the process, because data it's gold nowadays. And on top of this, there is, of course, like everywhere, security to ensure, as we said, that nobody can take advantage of all your work. Now I move to this slide, which on the other hand is, I've selected it to reassure you. I've chosen this slide because it's here to make you understand that you don't really have to implement all of this. Or maybe you have to implement this, but you don't have to implement every sub-block of this. Because of course, I get that you may not be interested in having all of the different functions, all the different applications enabled by a digital twin. Here are stated just a few, but there can be many more, such as process controls, prediction, fleet analysis, root cause analysis, reasoning. So there is the whole monitoring, diagnosis kind of applications. There are the predictive maintenance applications. There are the logistics and the engineering applications. You may not be interested to build everything everywhere all at once, which has just won the Oscar. And so what you need to implement, it may be just few of these blocks nowadays to start getting some of the advantages of the digital twin and be prepared for the next years. Of course, you need to have a physical and a digital twin. You can't escape this. And you have to connect the real world to the physical world, to the digital world, as we already said many times during this presentation. And you do this through these blocks. Then you see these tiles. So you can see that there are like sensors, which have to be connected through an IoT protocol. The IoT protocol on its own doesn't provide value if you don't link it to the data distribution. And this data distribution has to rely on trusted data sharing and some on other cyber physical equipment. The good news is that probably you have already implemented some, if not a lot, of these processes. So I am sure that many of you already have in-house the basics, at least for implementing a digital twin in your production system today. Of course, you can go further with virtualization options or some deep data knowledge link. This is optional. Of course, the more you implement, the more you can use it, the more it's efficient. But you don't have to take all the steps at once. Once you have the basic building blocks, the basic skills in place, then you can really start building on it by implementing different services, because once you have the data and maybe you don't have a digital twin prototype, but you have a digital twin instance, you can start to make, for example, to build on top, to connect on top of it, change detection applications, live monitoring applications, which with the correct front end will enable process control. Or you are not interested in this, you just want to have a digital twin aggregate. So you build a really basic digital twin instances, and through a live operation framework, you get your fleet analysis. You can see how you can tailor your digital twin solution to what are your needs. And this is where the research is working towards these days, to prepare the ground with a set of standards of interoperability protocols to make this more of a reality in the next 10 years, of course. I will present you now some case studies. We made some reasoning about what could be what could be the possible implementation possibilities and relative challenges for the digital twin in the railway sector. You may already thought of this. If not, we are scratching your mind. And then I will present you some assets made by Lynx in previous research projects. And I'll show you how these single assets can be made interoperable and together may build the foundation blocks of a digital twin instance. So you may of course have already thought of this, but yeah, it's good to refresh our minds. And so, according to what we have seen today, these are possible implementations of the digital twin in the railway sector and the value that can bring. For example, the first, it's the enhanced maintenance and services of trains and tracks through predictive analytics and remote monitoring. Of course, analyzing data from sensor and other sources, a digital twin can identify potential maintenance issues before they become problems. And you for sure see the value of this. This allows the operators to schedule maintenance and repairs more efficiently, and again, reducing downtime and improving the reliability, the overall perceived reliability of a railway system. How can we do this? We can do this through a mix of different digital twins, because here you can easily see how the digital twin instance comes into place, because you have to, again, to have a source of a global source of data from the single sensor installed on the train. And also we have the digital twin environment, because here we can use the digital twin of the train and the digital twin of the track globally through a digital twin environment to check how these two elements interact with each other. And so the one can improve the data that we collect from the other and vice versa. This is a very interesting concept that I think applies well to what we have seen today. Then we have the second point. It's of course increased efficiency and productivity through the real-time monitoring and optimization of the train operations. This is more relative to the digital twin aggregate, because when we know the positions of all the trains in the fleet in real time, and also we have the digital twin of the railway network, in this way we can run simulations. For example, if we have a delay, digital twin can provide the real-time data on train location, speed, and performance. So as I said, if we have a delay, this allows operators to run many simulations in real time and to run both simulation and AI algorithms according to the issues that is presented to operator, to And this leads to faster rescheduling of the available resources, and so we can minimize the impact of congestion or an issue on the track by, as we said, using the digital twin aggregate that pulls information from all the trains, and so we can actually make simulation that take into account the state of the whole railway and the single trains on tracks. Third point, it's very important, improve safety and reduce risks of accidents through the simulation analysis of possible potential scenarios. This is probably more relative to the digital twin prototype, more relevant to the train component manufacturers. In this case, if you implement a digital twin, again, as we have already said, you can run different simulations of all the components, and you can better simulate crashes, and so reduce the risk in case that an accident unfortunately comes. We can minimize its impact. Again, we also have some issues. So we have limited, nowadays, unfortunately, we have limited interoperability and standardization. And so this has to be addressed in the coming years. This is the main roadblock nowadays for the actual implementation of digital twins. The data acquisition process, it's still complex and time consuming, and you have to plan for it, requires integration of multiple sources and systems. We still have to improve on this. Also, there is the obvious economic investment and that you need to make, and so you actually need to have money to dedicate to this upfront. There are then implementation costs, both in terms of hardware, software, and you have to skill your personnel. So this all has obviously have to take into account, and this is why it's important to start experimenting today, because you have to be ready when the commercial software will be available. And then obviously when we are talking about data, there is always the privacy and security concerns related to the collection and storage of sensitive data, such as passenger information and train operations. This concludes one first part of the presentation. Now we switch, as I said, to a quick overview. I'll try to be not to go into detail, but I really want to present to you the results of these three projects. The first one is still ongoing. The first and the third are still ongoing. The second has just finished, but Lynx is involved in these three projects and has developed different components that I hope you understand, will make you understand our digital twin. It's not a monolithic component, but it's really made possible by mixing up all different layers that make the end user functions possible. So we go back to this figure, and now I will introduce you to Replica, which is a digital twin orchestrator. And so this component covers these two functions, and yeah, I will go through very quickly through this presentation. This component has been developed in the context of the Reclaim project, and it's a distributed framework to support the digital twin fault diagnosis and predictive maintenance solution for in this case, the industrial IoT environments. It provides a full infrastructures for hosting a digital twin implementation and specific APIs to integrate with different AI services and simulation services. This is important because you may already have AI and simulations in place. It's important that the digital twin can integrate with those. This is the architecture. As I said, I won't go into detail, but yeah, just the main components. There is this orchestrator, which is a software component that is in charge of managing these AI models and simulation. And we have the environments where these AI models and simulations can run. And then we have very important the external sources, because as we said, it's very important to link these models and AI models with good data. And so we have this adaptation layer for connecting to real-time data sources. If we think about the digital twin instance, for example, and the database, in this case, maybe we think about more about the digital twin aggregate. And of course, there is a front end that we won't spend time on. But it's interesting, the concept here, just to understand how it's important to be able to dynamically manage simulations, because digital twin is a very complex object, modeling a very complex physical object often, so you really need to implement different simulators and different AI models. And so you need to scale this also across different computing environments, because you can't really run on your local infrastructure. You need to scale this on cloud infrastructure. So it's important to plan in advance for computing resources, for example. And so we have this AI environment that allows to run the AI models according to the ERCI requests that come from the simulation environment or from the user. And you can use, in this example, models that come from an AI marketplace. Again, this is where a lot of standardization is happening right now, to make possible that the AI models can be shared, and you can actually buy on-the-fly models to run simulations to the topics that you're interested in that particular moment, to have an evolving product. The digital twin orchestrator, as I said, it's the manager of these AI and simulations, and you can see that it's in charge of linking those with the data and all the external services. In this case, it's based on Apache Kafka, very interesting software module that we may discuss in another occasion. And you see there are two possible scenarios: the one where AI models are driving requests for simulations, and there is also possible the opposite scenario, where we have the simulations requesting AI models and use their results as part of the simulations. Let me go back just 1 second to this slide. You see how these AI models and simulations can't be used on their own. They need to be used in a feedback loop together, because each one can make use of the other, because you more often than not cannot describe a process only through maths or only through a black box that doesn't know anything about their underlying process. The real use case scenario is more often a situation in which you know something about the underlying process and something you don't. And so in this case, you use both of these tools inside of your digital twin. Next step, as I said, this is still under development. As we said, we are active also in the standardization field. I think this is where a lot of work will go, because now we have the computing infrastructure, we have the tools, we have the concepts. Now we really need to start to make all of this software interoperable, and so that you can really build the digital twin solutions that is most suited to your needs. Next, we have another software component, which this time is coming from the EFPF project. This is the deep learning toolkit, which serves the purposes of live monitoring, behavior assessment, and prediction. This component makes use of deep neural networks techniques to improve the maintenance processes and to prevent equipment failures. This tool has been used on an edge banding machine inside a furniture factory to monitor it and predict failures using sensor data to monitor the machine, and by applying deep learning methods. Deep learning methods are the AI models that we have talked about, and they need a lot of data. So it makes a lot of sense to use this module inside the digital twin, because there you really have access to a lot of the data. Yeah, I won't go in detail, but let's say that for predictive maintenance, the goal is to use to train the AI models to predict the target for the future using actual data. So when you already have collected the data, and if you know that a failure is going to happen, then you can use this information to use the current data to predict for failures in the future. And this is exactly what we did in this project. It was very successful. We achieved a binary prediction where we had an output at 0. So the tool doesn't think that will be a failure. 1, we think that it will be a failure. Very simple, but this was what was requested by the end user, because this was actually used by the shop floor operators along with a confidence score for each prediction to optimize their scheduling of downtime to reduce the unplanned downtime. And so, yeah, there was also a GUI, very easy to use, and also allowed for visualization of the data. So you can understand how this is relevant in the context of a digital twin instance. Last component I want to show you today, it's under development in the knowledge project, and this component is in charge of data distribution, trusted data sharing, and to ensure fidelity of the data. Very important concepts, as we said. We have this data quality platform that from the raw sample that is collected from the IoT infrastructure takes care to apply validations to it to make sure that this data is useful for AI applications. Data which is marked as and not valid, sample not validated or not validated, they are dropped because they can actually, as we've seen, be dangerous. Again, this is a demo of how it works. We have sample topics here as a sinusoidal wave. Here you can see that there are spikes added to it, and these spikes are automatically detected and removed, so that the AI process that needs to learn about this process doesn't learn about also the spikes that are actually just noise. This is already possible. This also implements some checks on the data model interoperability by querying a database with the schema of the data that is expected to make sure that no spurious data is added to the system that will make the database noisier and more useful, more difficult to use. This is based on Kafka as well. As you see, there are many queues and it offers a lot of extensibility possibilities to really customize this to the needs of a particular use case. There is a front end here as well. Okay, so in the end, what I wanted to show you was this, that through different applications that can be made work together, even if we don't have built a digital twin on its own, we actually have done it because we are covering most of the building blocks of the digital twin that are required in this case to enable predictive maintenances. If we had different tools, we could build different things together. Now the work that we have to make us and the whole research community, it's to work on standardization to allow these tools to be always more interoperable and to be mixed and matched according to the needs of the users. Now I think we have some time for a very quick demo. This demo, it's we can share data coming from use cases. So I will show you data that we have used for testing purposes. This is a water pump data set that has been made by collecting data coming from a pump. There are in this case 52 sensors applied to this pump, and each sensor pushes data with the corresponding timestamps. The sensor has been collected for 5 months, from April to August. In this case, it's stated in the specifics of the data sets. And we have sensor readings every minute for each sensor. And unfortunately, what a parameter is measured is not specified. In total, we have a lot of data points, you can see. Unfortunately, we only have, you can see from the first figure, only few information about breakages. And you can see also in the second figure, the class distribution. Most of the time, the pump is working as expected, and it has been broken only 7 times, which makes this quite a challenge for learning the behavior that leads to breakages. Now, I will spend some time on this list of questions because these are the steps that we take every time we need to approach data analytics problem. We need to know what we are trying to predict. Do we already know what we are trying to predict, or do we have to find patterns without guidance? In this case, we do, but the data is not clearly labeled, and so it's more of a mixed case. Is the predicted data, variable data, completely useful? Again, there are no data quality in places for who collected the data set, so yeah, we cannot make this assumption. Is the prediction outcome a number, or yes and no? Let's say that it is a yes and no, but it's a more of a categorical answer, because we have 3 states: normal, broken, and recovering. How frequently is the predicted variable recorded? In this case, we know every minute. And does each sensor measure have an associated variable, or are they aggregated? In this case, it's not clear, because the sensors, it's not clear what they are measuring. For some sensors, we only had like the data, and we don't have any metadata about it. So it was a challenge also in this way to understand which data was actually useful, and is prediction outcome clear, or do we have to define what is normal and what is broken? In this case, we already knew. But according to the information that we have presented today, I think you can see where I want to go. And this is really the value proposition of a digital twin, in this case for the predictive maintenance applications. Because if I was working with data coming from a digital twin, I would already have the answers to all of my questions. A digital twin can give me all of these answers, because these are not simply randomly attached sensors to a pump, which I don't know where it is, I don't know the manufacturer, I don't know anything about it, but this is complete data. And this is really what I was wanting to highlight today, the value of the digital twin, because it can really speed up the development of such applications. Really, when we had to implement our predictive model on this data, this is what we were presented. A lot of really noisy, unlabeled data that you have to make an understanding of what label can you apply to this data, what variables are they monitoring, is this data actually reliable? So you have to really waste a lot of time performing data analysis and run some algorithms before you can make a decision, and then implement your AI models. Okay. I think that we can, no, maybe I have the time, so I will stop sharing the presentation and I will share the screen. Because I think this can be interesting as well. Okay. Okay, you should now see my screen, and this is the demo of the predictive maintenance application. I think it's interesting also to see some more technical stuff. In this case, we use Python language. This is a notebook where we run experimentations. And this happens after we have done all the hard work that a digital twin would have made us very much easier. So what a digital twin enables us to do, it's to simply load a model, as we have shown you in both in the replica architecture or in the deep learning toolkit predictive maintenance tool. And so in this case, we have some testing data. We have a ground truth of a failure, and we want to see if our model was actually able to predict the failure. And so this model, it's a binary model. We have trained it this way. Again, if we were to use a digital twin of the pump, we would have many more options because we will be able to operate quicker. But the simple thing is that if this probability one variable is greater than 85%, because AI models have always a confidence on the predictions, then we assume that we have a failure. As you can see, the model has already computed the results for 20,000 minutes in the future, and so we simulated quickly. And here we have the ground truth with the green color. It's 0 means that the pump is operating correctly. 1 means that the pump is operating it's broken, it's defective. And you can see that our model, the prediction is in red. Here, predicted the failure, which didn't actually happen. And then after some time, predicting again a failure that this time actually happened. And so I think that another lesson that we can take about why digital twins are useful is that if we have some knowledge on the physical manufacture, we can also better interpret the results of the AI models, because it's easy to label this false positive prediction as an error of the AI models. But if we had a digital twin, we would know the conditions in which the pump was operating at the time. And so maybe the pump at the time was already expressing some signs of strain. And so an operator could have scheduled some maintenance in this interval between when the first breakage was predicted to when the breakage actually happened sometime later. But we don't know for sure because we don't have a digital twin behind this pump. So I think this is the most important concept to take away from this example, which again uses real data and real predictive models. So let me go back to the slides. We still have some slides to present, not a lot, I promise. We are getting towards the end. Okay, let me get back to the conclusions of our presentation for today. Okay, I want to spend just some more minutes on the future of digital twins and the potential impact that they can have. Let me just make some remarks on these emerging trends that we are actually researching on right now, which is digital threads. Digital threads can see as a complement of the digital twin because they are this data-driven approach that connects and integrates all the information relative to a product or a process throughout the whole life cycle. So this is also relative to the research, the active research on the digital product passport topic, because the goal is also to integrate with blockchain systems, have to have this. It's more than a database because it's a collection of data sources, but that can be accessed through a unique endpoint and provide all the information from starting from the requirements collection phase to the design, the manufacturing, the testing, and the maintenance of the product in a very consistent and traceable way. This is a step beyond of the different data sources that nowadays, when implementing a digital twin, you have to connect single one by one. The goal is again to work on interoperability and to build these kinds of solutions. We think that this research area will be one of the enablers of the digital twin, because if we solve this problem, that it's very hard at the moment. It has a huge impact on the development of digital twins. This will speed up a lot the adoption of digital twins. And also, I want to introduce you the concept of the industrial metaverse, which you may already know, because we think that one of the possibilities enabled by digital twins, other than what we presented to you today, will be again this possibility of accessing all of this data, all of this information, not only through the standard way that we are used to, so with the mouse and keyboard and through different software, but to have a more holistic access across both the data and the processes, and to be able to link these processes and data with 3D models and to really see what's happening in your product across the whole life cycle, from manufacturing to testing to the actual operation. So we think that this is another very interesting area for research. This graph, I think I've recently seen a paper, as Silvio said, which tries to make a grasp of what's going on with the adoption of AI, which is the core of the digital twin nowadays. Because useful new technologies generally follow a sigmoid curve. You have here slow takeoff as the technology is invented and all the major pains get sorted out. And then you have this really incredible explosion of growth as people find it useful and the technologies get better and better and better and better. And then you start to have competitors entering the market, and people find by using the technology, more and more real-world practical uses for it. And after this step, there is a massive race to make newer, better, bigger things. And at the end, you reach the limit of what's possible with a specific technology, and the rate of progress flattens again. I want to leave you with a question, because I don't have the answer for this. And so, at which stage are we today with digital twins? Are we at the beginning of the sigmoid curve? Are we in the middle, or are we in the end? I don't have the answer. Thank you for your attention. If you have any questions, I'm happy to try to answer them.
Thanks, Edoardo. Time is actually running, so I believe there's no time for questions immediately, but feel free to send us an email. I will share the context.
Yep.
So okay, here you can see the context from Florence that introduced the technological analysis, from Edoardo that has given you this tutorial, and from myself for more general questions. Feel free to drop us an email for any further question you might have, any further curiosity. The purpose of this tutorial was to, given the fact that hopefully we all understand and we all are aware of the fact that this type of technology is coming, probably even a bit faster than we might expect. The purpose is to understand what are the competencies that we need to have, not necessarily to develop digital twins, but at least to understand what are the steps that we need to take to adopt digital twins in our processes, and to talk with technological providers the correct way. Because I've learned that to a wrong question, you can only get wrong answers. So have the basic competencies for asking the correct questions to different type of technology providers will help us to get the correct answers. And as you've seen, digital twins as artificial intelligence rely on a wide set of underlying competencies, either physical modeling competencies, or Internet of Things, or sensing or monitoring competencies, artificial intelligence competencies, programming competencies, and we can go on for quite a long time. And so we are really willing to help the ones of you that are in need to create or to adjust their own roadmap for adoption. So feel free to get in touch with us anytime for any further inquiry you might have on this topic. Last but not least, I will just give you a very quick overview of the next events that have been planned by the STARS Consortium. So in March, at the 23rd of March, there will be a webinar jointly organized by the ERCI and STARS that is named Using Data for Improving Safety in Rail. Then on the 19th of April, we will again, Links will hold a tutorial on cybersecurity of connected objects. As Edoardo mentioned, this is one key aspect of the digital twin, because information on the physical, on the original physical body to be measured and to be mimicked by a digital twin is made by means of connected objects. And so these connected objects need to be cyber secure. In mid-April, there will be an hacking match event organized by the STARS Consortium named Blockchain for Railway Processes, Products and Services, to which you can contribute both by issuing a challenge and as participants. And then we'll have another 2 tutorials, one on the 4th of May named 5G for mobility applications, and on the 11th of May, sustainable development in railway businesses. So this is all from our side. We are concluding this event right on time. I thank everybody for participating. You will receive in the next few days the slides that have been presented today and a link with the complete registration of the tutorial. Thanks, everybody.
Thank you. Bye.
Thank you. Bye-bye.
Thank you.
Bye bye.